Physical and chemical changes. Some of the most useful and powerful properties of matter are those related to how and why matter changes. There are countless changes in matter that affect us every day. For example, applying heat to an egg, burning gasoline, freezing water, and mixing oil and vinegar, to name a few. Understanding and categorizing kinds of change are an important first step to making use of change. You can discover a great deal about matter simply by observing a candle. The physical properties of the candle include its color, texture, and density. Properties that do not affect the ability of the wax to change in any way. However, some other physical properties do change wax. For example, the wax melts at a definite temperature, called the melting point, and then changes to vapor at a temperature called the boiling point. These physical properties affect the ability of wax to undergo physical change. The wax, whether solid, liquid, or vapor, is still the same substance. As the candle burns, you can observe another kind of property that affects change in the wax: combustibility. Candle wax burns, producing heat and light. Combustibility is a chemical property. It describes the ability of the wax to react with oxygen to produce new substances. Unlike physical properties, chemical properties always involve change in a substance. Some of these changes are illustrated in Figure 1. Let's go to Figure 1. The wax of the candle is undergoing both physical and chemical changes. Which change results in new substances? Which does not? Physical change. In a physical change, the substance involved remains the same substance, even though it may change state or form. When the candle wax has melted or vaporized, it is still wax. Changes of state, melting, boiling, freezing, condensation, sublimation, are physical changes. Also, the opposite of sublimation is deposition. Figure 2. Changes of state. You can see how you have the three phases: solid to liquid to gas, and going from gas to liquid is condensation, going from liquid to solid is freezing, the opposite is melting, of course. The opposite of condensation is vaporization, and going from a solid to a gas is sublimation. And don't forget the deposition, which is the opposite of sublimation. You can see a physical change when you pour melted chocolate over ice cream. Liquid chocolate forms a thin, even coating over the ice cream. The chocolate becomes solid as the ice cream cools it. But once it's in your mouth, it tastes the same in both states because its particles have not changed. Dissolving is also a physical change. When you dissolve sugar in water, the sugar particles spread out, but they are still there as sugar particles. You can reverse the process by evaporating the water and collecting the sugar. Most physical changes are easy to reverse. Chemical change. In a chemical change, the original substance is changed into one or more different substances that have different properties. As the wax in a candle melts and vaporizes, some of the wax particles join up with oxygen from the air. The result of this chemical change is the production of water vapor, carbon dioxide gas, heat, and light. The wax particles that seem to disappear are actually changing into something else. Chemical change always involves the production of new substances. Most chemical changes are difficult to reverse. Burning, cooking, and rusting are all examples of chemical change, as is shown in Figure 3. Figure 3, a chemical change produces a new substance with new properties. The red-brown copper of the surface of this roof has changed to a new green substance. Chemical or physical? You can see the chemical change in the wax just by looking at the burning candle. So how can you tell if a chemical change has occurred? The clues listed in Table 2 can help you decide. So here's Table 2. Clues that a chemical change has occurred. A new color appears. Heat or light is given off, such as a match. Bubbles of gas are formed, such as magnesium and an acid, or calcium and water. The solid material called a precipitate forms in a liquid. For instance, if I mix lead to nitrate with sodium iodide, I form a precipitate, a very bright orange-yellow precipitate called lead to iodide. The change is difficult to reverse. For instance, once I burn a match, it's difficult to get the wooded match back. But do not come to any conclusion too quickly. All of these clues suggest that a new substance has been produced, but any one of them could also accompany a physical change. You must consider several clues in order to determine what type of change has taken place. Okay, let's look at Figure 4. Figure 4 relates to understanding concepts, but let's read Figure 4 before we read understanding concepts. Operating a car involves many changes, so there are 5 listed. Let's look at them individually. A, in the fuel injector on top of the engine, changes occur as gasoline evaporates and mixes with air. B, inside the engine cylinders, the explosion of the gasoline-air mixture produces hot exhaust gases, including water vapor, carbon dioxide, and nitrogen oxides. C, the exhaust gases pass through the catalytic converter where some harmful gases are changed into safer new gases. D, the exhaust passes out the tailpipe. On a cold day, steam from the exhaust condenses into a white cloud, and that white cloud is actually condensed water vapor. E, as the steel of the car is exposed to air and water, a crumbly reddish brown substance forms. The steel has changed to rust, which is iron 3 oxide. Understanding concepts. Explain how physical change differs from chemical change. That's simple. Physical change does not change the underlying substance. If you reverse the physical change, you get the substance back again, where in chemical change you do not. Classify each of the following as a physical or a chemical change and explain why. Garbage rotting. Bacteria is breaking the garbage down into a variety of different substances. Cutting up carrots. You're just turning whole carrots into diced carrots. It's still carrot. You taste the whole carrot or you taste the diced carrot, you still taste carrot. A silver spoon turning black. That's tarnish, probably silver sulfide. So you're forming a thin coating of a compound called silver sulfide on the outside of the spoon. It's chemical. Making tea from tea leaves. You're just simply dissolving material from the leaves into hot water. It's called an infusion. It's physical. Bleaching a stain, probably chemical, because you are literally changing the stain into another substance, or you could be changing the pH and changing the color of the substance. A color change often indicates chemical change. Boiling an egg. Well, that's a tough one. You're actually denaturing the protein. You're changing the protein. In many ways, it's still the egg, but the white of the egg is a globular protein, and you're denaturing it, and it's becoming less dense, turning white from clear to white. It's still the protein, but it underwent a physical change that's very difficult to reverse. That's a tough one. During a power failure, Blair lit 4 identical candles. He placed 3 candles very close together on a table and 1 on a different table. When the power came back on an hour later, Blair was surprised to see that the candles in the group were much shorter than the one by itself. There was also more melted wax around the base of each of the 3 candles. Account for Blair's observation. What kind of candles should you keep on hand for emergencies? Well, the 3 candles may have gotten, as a group, hotter, melted faster. If you're going to have a power failure, you may want to have big fat candles around that heat more slowly. What was the temperature of the room when the candles were melting? So a lot of variables could go into that. Making connections. Which of the changes described in Figure 4 involve chemical change? Well, certainly the explosion in the cylinders B, the catalytic converter, you're changing it into harmless or more harmless substances. E, the rust of the car, that's chemical as well. For each identified change, determine the impact it could have on the environment. The physical changes was the evaporation of the gasoline, that was A. D was the condensation of the steam. So B, C, and E were chemical. And in terms of, for each identified change, determine the impact it could have on the environment. I'm going to leave that to you, and we'll discuss that in class. Which change must car designers pay attention to in order to minimize damage to the environment? Well, when I was a kid, they didn't have catalytic converters, and that's helped with pollution a great deal. They can get even better. And pollution standards have to be more uniform around the world in order for us to combat pollution, because air pollution does not observe political boundaries, political borders. Reflecting. Go back to the list you've brainstormed for getting started on page 13. Write beside each change on your list, whether it is chemical or physical. If you are not sure of any, just leave a blank space. You can return to your list as you work through this chapter. Corrosion. Have you ever wondered why metal car bodies rust but plastic bumpers do not? As you know, different substances have different physical properties such as color and hardness, and different chemical properties such as combustibility and reactivity with acid. One chemical property that has great economic importance is the tendency of a substance to undergo corrosion, the slow chemical change that occurs when a metal reacts with oxygen from the air to form a new substance called an oxide. And when we talk about corrosion, we're really talking about the main one, rust and preventing rust, which is iron becoming, or steel, iron or steel becoming iron 3 oxide, which is rust. Kinds of corrosion. The most dramatic example of corrosion is rusting, which I just spoke of. The reaction of iron with oxygen to form iron oxide, iron 3 oxide. Iron is usually found in the form of steel, a mixture of iron, carbon, and other substances. This alloy or mixture of metals is much harder and tougher than the original iron. Rusting is a chemical change that involves iron, oxygen from the air, and water, as well as the salts or other minerals dissolved in the water. Every year, millions of dollars of damage are caused to building structures, vehicles like the car in Figure 1, and other iron and steel products due to this process. Rust is particularly damaging because of one of its physical properties. Rust is porous, absorbing water almost like a sponge. As a result, it dissolves or flakes off, leaving another layer of fresh metal underneath to be attacked by oxygen. The process continues until the rust has eaten its way through the metal. By contrast, aluminum has a similar chemical property in that it also reacts with oxygen, but the aluminum oxide that forms is strong and unaffected by water. The corrosion stops and the oxide acts as a protective coating. If you have aluminum cooking pans at home, you will be familiar with the grayish, dull coating of aluminum oxide. Even silver develops a surface coating of tarnish if it comes into contact with sulfur-containing foods such as eggs or mustard. The black coating seen in Figure 2, silver slowly corrodes in air, is silver sulfide. Silver tarnishes slowly if left out in the air. The more sulfur-containing pollutants in the air, the more quickly it tarnishes. The black layer can be removed by polishing the silver. It must have been terrible with the sulfur-containing coal in the turn of the 19th and 20th century in the wealthy homes where they had a lot of silver, and the maids and butlers, and they had to clean the silverware, but it must have tarnished very quickly in those days. Preventing corrosion. There are several ways to prevent corrosion. One method is to paint the surface of the metal. Figure 3. This is a job I would not like. Some bridges are so large that painters take years to finish the whole structure. Then they have to begin again. As long as the painted surface is not broken or cracked, oxygen in the air cannot get to the metal. For the same reason, cars are often sprayed with oil to coat the bottom and inner surface of the car body. Iron can also be protected by coating it with other metals. Some metals have the chemical property of being easier to corrode than iron. This property is used to protect the hulls of ships and motorboats. For example, as seen in figure 4, a plate of zinc is attached to steel boat motors, figure 4. Another metal attached to a boat motor can protect it from corrosion in a process called cathodic protection. The steel motorboat remains untouched as the zinc is slowly used up. The zinc is replaced when it has completely corroded. A special alloy of steel made by mixing iron with nickel and copper is now used in some building structures. The metals corrode quickly, but the nickel and copper oxides form a protective layer that prevents further rusting. Another way to prevent corrosion is to use metals that have different chemical properties. Plastics are being used increasingly in car bumpers and panels that get frequent bumps and scratches. Steel loses its strength if air and water penetrate through a scratch in the paint. But plastics never corrode and remain strong and flexible. Understanding concepts. What is corrosion? The slow change of a pure metal into various other compounds. How is an oxide formed? Chemically. Describe two processes that form two different oxides. Well, you can form aluminum oxide when aluminum is exposed to oxygen. It's a spontaneous process. You can also form iron 3 oxide when iron is exposed to the moisture in air. Make a poster describing 3 ways to protect a metal from corrosion. I'd like you to do that. We'll talk about that assignment later. Making connections. Corrosion of automobiles causes millions of dollars of damage every year. Which parts of the automobile corrode the most? Why? I would say the undercarriage. The road salts, especially in the northern interior areas where road salts are used, or in the more tropic areas, you have near water, near salt water, you get a lot of corrosion at the bottom of the car. What decisions or steps can you take to protect these products from corrosion? They use an undercoating, a tar-based, heavy-duty paint that they put on the bottom of cars to prevent corrosion to the undercarriage. Reflecting. Engineers design pipelines to carry oil or natural gas over hundreds of kilometers, such as the Alaskan pipeline, enormous. These pipelines are made of steel but do not corrode. The engineers attach other metals to the pipelines every kilometers or so. How does this protect the steel? It simply outcompetes the steel for electrons, and you don't get the conversion of the steel to iron oxides. Combustion. What chemical reaction occurs in the gas furnace that heats your home? Could be methane plus oxygen, forms carbon dioxide and water. If it's a blue flame, like on the top of your stove, it's a fairly clean flame. What kind of chemical reaction occurs when you light a match? What caused the forest fire in figure 1? Some combustion reactions are destructive. Forest fires consume thousands of hectares of land every year in Canada. A hectare is a unit of measure similar to the acre. It's 100 meters by 100 meters square. Also in Northern California, you had a lot of fires this year in the United States, terrible fires. Burned thousands and thousands of acres of land, hectares. What makes a car engine work? These and the fires shown in figures 2 and 3 are examples of an important type of chemical reaction called combustion. Figure 2, the quick reaction of magnesium with oxygen is combustion. Magnesium is often used as a component of emergency flares, which produce a bright light even in rain or snow. Also sparklers, they're used in sparklers. Figure 3, fires can rage for months when oil wells burn out of control. The fires can be extinguished using explosives and other methods that steal the leaking oil and consume the oxygen that feed the flame. Which component of the fire triangle is removed to stop the fire? At the end of the first Gulf War between Iraq and the United States, Saddam Hussein lit many wells in Kuwait on fire and had to be put out over a long period of time. It caused catastrophic environmental damage. In combustion, a substance reacts rapidly with oxygen and releases energy. The energy is observed as heat and light. Many substances such as wood, kerosene, and diesel oil burn rapidly in air, which is only about 20% oxygen. This makes them useful as fuels. Figure 4. The fire triangle is a convenient way to remember the 3 components of any combustion reaction. Removing any one of these makes the triangle incomplete and puts out the fire: oxygen, fuel, and heat. Fossil fuels and combustion. Coal, oil, natural gas, and gasoline are all fuels. They are called fossil fuels because they were formed from plants, animals, and microorganisms that lived millions of years ago. When these organisms died, they did not decompose completely. Instead, they were buried by sediments, and the energy in their cells remained locked up. Human technology developed over the centuries depend on these long-buried organisms. Their stored energy powers homes, industries, and various means of transportation. When any fossil fuel burns, the main product of the reaction are called carbon dioxide and water vapor. That's if they burn completely. The particles that make up fossil fuels are called hydrocarbons. To represent the combustion of a fossil fuel simply, the following word equation can be used. Hydrocarbon plus oxygen yields carbon dioxide and water. In a word equation, the substances you start with are written on the left and are called the reactants. The resulting substances written on the right are called products. Combustion and air pollution. Under ideal conditions, the combustion of hydrocarbons produces only carbon dioxide and water. But ideal conditions rarely exist. Fossil fuels are not pure hydrocarbons, but rather are mixtures of many different substances. Also, the chemical action of combustion can be less efficient if there is not enough oxygen or heat. When not enough oxygen is available, 2 other products may be produced: carbon monoxide and carbon. Carbon monoxide is a poisonous gas that you will learn more about in section 2.8. When gasoline burns in an automobile engine, the carbon dioxide that is produced increases the greenhouse effect, which may be causing global warming. That's figure 5. Let's look at figure 5. Carbon dioxide gas produced by combustion in industry and automotive engines increases the so-called greenhouse effect. The glass panes of the greenhouse allow sunlight to pass through but prevent heat from escaping. A similar situation occurs in the atmosphere. Carbon dioxide in the atmosphere acts like the glass in the greenhouse, trapping heat close to the Earth's surface. Many scientists believe this is causing a gradual increase in Earth's temperature. So, the visible light has short wavelengths. It passes through the glass, is absorbed by the Earth, by terrestrial things, water, people, rocks, trees, and then it's re-radiated as heat. Now, heat is infrared. It has a longer wavelength, and that bounces off the carbon dioxide back to the Earth, and that causes the greenhouse effect. Methane, CH4, is 25 times more powerful as a greenhouse gas than carbon dioxide. Now, as the Earth warms, the tundra up north will melt. Siberia, northern Canada, and that melting of the tundra will release tons of methane gas into the atmosphere, producing an extraordinary greenhouse effect. So it's not a question necessarily of carbon dioxide, but of other gases that have to be controlled as well. Other products include carbon monoxide, smaller hydrocarbons, sulfur dioxide, and nitrogen oxides, all of which can harm people and the environment. In fact, combustion is the major source of air pollution in the environment. Now, understanding concepts. What is combustion? A hydrocarbon plus oxygen, anything plus oxygen, that's going to produce a substance plus a lot of energy. For instance, magnesium and oxygen. 2A. When fossil fuels burn, what are the reactants? The fossil fuel plus oxygen. What are the two main products of this combustion? Carbon dioxide and water, if it's a complete combustion. Why are other products also formed? Incomplete combustion. Illustrate which part of the fire triangle is removed when each of the following methods is used to stop combustion. Closing the valve on a propane tank that supplies propane to a barbecue, the fuel. Dropping and rolling if your clothing catches fire, the heat, the oxygen. Pouring water onto a campfire, oxygen. Pouring baking soda on a grease fire, oxygen. Blowing on a flaming marshmallow, heat. You're depriving it of oxygen as well. Making connections. Why should you never operate a gas or charcoal barbecue inside a building? You can produce carbon monoxide. And the carbon monoxide is not healthy to rebreathe either. But carbon monoxide will outcompete oxygen in your blood. Explain why building codes require an external source of air for fireplaces in new homes. Because if you use up all the air in your home, then what are you going to breathe? Exploring. Fossil fuels may be obtained from the black oil that is pumped from oil wells. Use the internet to find out how these substances are found and separated. Some key words you might want to use in your search are petroleum, fractionation, fractional distillation, and oil refining. Reflecting. Wood is combustible, but chalk is not. Is combustibility a physical or chemical property of a substance? Combustibility is most assuredly a chemical property of substances. Why? Because you're changing substances. If you take a fossil fuel, you're changing it into carbon dioxide and water if it's complete combustion. It was a pleasure. That's the end of chapter 1. I hope you've enjoyed it. Have a great day and goodbye.